Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitaurus. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
All right, we're ready for our final session of the first half of the morning. Right now, it's going to be implementing the post-quantum survivors, a retrospective. This is going to be presented by David Hook, VP Software Engineering at Keyfactor, also a founder and still active committer of the Legion of the Bouncy Castle Cryptography Project. So please join me in welcoming him to the stage.
So I'm just going to make sure I'm holding this the right way up. There we go. Excellent. So basically what I'm going to talk about today is two things primarily, but it also leads to a third. I've been fielding a few questions about, how Bouncy Castle actually acquired the post-quantum implementations and what we did to actually get them. So I thought I'd try and answer that question now. And the second question, because a lot of people ask, how do you know these things are correct? What are you doing to try and maintain that? So this looks at what we did originally to verify correctness on the algorithms. And it also looks at things that are actually happening now. And it really does serve as a reminder that, as a lot of other speakers have emphasized, with the post-quantum stuff, we really are on a continuous journey. This isn't about just migrating to a new set of algorithms and stopping. Stuff is continually happening. So basically, what happened originally was that a group came to see me from the Australian Cybersecurity Centre and said, NIST's in round 3, you guys have a few post-quantum algorithms already, are you interested in actually adding them? And we were, of course. And so they actually made funding available to us. And what that meant was that we actually ended up running a project that involved 3 Australian universities, plus our developers, to actually add all the NIST round 3 finalists. So we'd already written a couple. One of them had already been done by me. Thanks to COVID, I got stuck in my bedroom for a week with my wife sliding pancakes and flounder under the door because that's all that would fit, and implemented Sphinx Plus. The others, of course, Roy had actually already done work on Sabre as part of his postgraduate. Monash University and the University of Wollongong had groups that were actually doing things with lattice and also multivariate polynomials and code-based cryptography as well. And finally, we also got review work funding, and the review work was conducted by a research team at the University of Adelaide led by Yuval Yoram, whose name will appear again. And because this was sort of a government project as well, we actually got a project manager group involved, and they were from Tara Schwartz. Of all the things that actually happened, the project manager kind of fell apart very quickly because the people from the team were more used to dealing with, I guess, regular IT contractors as opposed to goofy open source programmers and a team of postgraduate students. So I actually ended up doing the project management. But anyway, so we kicked off in mid-February 2022. And we scheduled the review work with the Adelaide team for July 2022 because they were actually trying to automate some of the review stuff. Part of the goal of the actual project was to build a tool which could be used that was automated for doing code analysis. And then we got the first couple of algorithms actually completed by the end of June. More algorithms were finished by the start of July, and we basically just made it with Kyber and everything when the actual finalist was announced as being Kyber, Dilithium, and Sphinx Plus. So there were a few things that came up, of course. I mean, one of the things was that because we were basically working off drafts, not everything that was actually in the documentation was the same as what was actually in the reference implementation. So we found that it was actually necessary to develop using both sets of things as documents. So the reference implementation was as much documentation as the actual documentation was. The CAT data stuff in the reference implementation originally, there were a couple of the sample sets that were given where they were actually using machine-generated randomness, which made it almost impossible to actually regenerate the CATs properly. So there were a few things that we had to sort out. And yeah, the use of the NIST CAT random was actually inconsistent across the APIs. In some cases, it was used one way. Other cases, it was actually used as a seed generator in its own right, which then fed into something else. If you didn't pick that up, again, you found your CATs were actually wrong. Of course, we had to make changes to the BC APIs themselves to incorporate the new features of the post-quantum set. The most distinctive one of those, of course, being the actual chem construct, because it's actually kind of halfway between key agreement and key transport. And then there are other things too. Composite at that point had actually appeared. There was a draft standard for a thing called external keys, which since died. And the other thing, of course, was that we were trying to actually do this so that it was more or less the same in both C# and Java for the low-level APIs, so that both the, primarily for us, so the implementations were easy to explain, easy to document, and easy to adapt to our other APIs. And also just simply for the fact that what we did was we actually got the students to implement Java or C#, depending on what the language of preference was, and then they actually did the other language as well. And the handy thing about that was that in terms of actually catching bugs and doing code review, the act of actually translating from one language to another does seem to cause people to review what they've done quite well. So we actually sorted out a lot of issues early just by virtue of the fact that we're actually doing two languages at once. Because while Java and C# do look quite similar, they're not quite similar enough for you to be able to mindlessly just copy and paste things. Rightio. So, of course, this is before Java 21. There were a bunch of things we had to do to basically shoehorn things in. We ended up using the Cypher and the key generator API. I mean, signatures, of course, were fine, but the issue, of course, was the chem. And there's a couple of ways of using chems. The reason we ended up using Cypher was that the IETF already had an existing standard for how an RSA chem was used, and our assumption at the time was that that would be followed. But actually, in fact, they came out with a new RFC, which actually was published late last year, for actually doing proper chems. And there's an actual chem recipient info structure now for CMS and cryptographic message syntax, which will be used in SMIME as well. So it's slightly different. But yeah, that was different. But it worked, which was nice. And eventually when the chem stuff arrived in Java 21, we were able to add that. So I'll just skip through this one quickly because I really want to get on to the refinement stuff. But yeah, again, this is the thing, with PQC, all sorts of things started changing. And Composite, of course, as we know, has actually just gone into publication. So we'll actually see that as an actual standard early next year, probably around January, February. External keys, which is something I think which will eventually come back. A few of you would be aware that there's also a standard coming for doing zero signature trust anchors, where your signature's basically left out, because usually with trust anchors we don't bother validating the signature since it's meaningless. And of course with post-quantum algorithms, the signatures can be quite large. The same thing applies to public keys. For example, if you're using classic Nicolease, which BSI are in fact standardizing, a public key can actually be 1.3 megabytes. which is a bit large. So the external key idea was basically you would have the key just stored as a hash, and then you'd have some sort of key server or whatever that actually provided the real public key. So your certificate would be used for establishing identity and all that sort of thing, but when you actually needed the public key to encrypt with, you'd get it from somewhere else. And there is actually kind of an example of that. This particular draft has survived in a sense. If you look at Merkle tree certificates, you'll actually see that the TBS structure in there, it doesn't use the actual public key, it uses a hash. So the actual initial review work, as I said, it was done at the University of Adelaide. The implementations at the time were reviewed at 2 levels, so obviously they'd only spent a certain amount of time on the tool. It wasn't that sophisticated, but it was more or less working. So they used the tool, and then they also checked things like the CATs, and they did hand checking as well to, look for what would be regarded as common security issues. The nice thing about the automated tool, of course, was it's static. So it wasn't a situation where you had to benchmark something or run things for a long time to work out what was going on. We'd actually find issues just by parsing the code. There were a few examples of secret leakage and everything due to side channels, which were actually detected in this process, and we fixed those immediately. And by 1.73, the experimental PQC implementations basically were, as far as we could tell, constant time and not leaking secrets. The other problem, though, that we had was, of course, the static analyzer really only worked with Java. And so what they did there was they actually did the Java analysis first, generated a report for the Java implementations, and then they used the C#. They checked the C# by hand by relying on the fact that basically the same people have written both code, and usually what happens when we do something in one spot, we do it in the second. That served us well. Now, what happened then was a number of years went past to this year, and various people had changed universities, but the actual research has continued. So I was contacted by the lead researcher who was originally in Adelaide and is now in Germany, just to give you an idea how things can change, in July, and they developed this product called Robusta. Now, Robusta, of course, there's obviously a caffeine-based theme to this name, and yes, it does work off Java code, although you could apply the philosophy, I think, that it uses to other things. There's a paper in progress now which will be presented soon, so there are some things about what we've done that I can't talk about too much because I'm leaving it for the researchers to actually present properly. But I can give some general ideas about what's going on. This is the list of organisations, and as you can see, there's a reasonably impressive team of people behind it, plus their postgraduate students. So Robusta is a lot more thorough. It works off the bytecode. So essentially, in fact, it works off a representation of the bytecode. But this actually allows them to actually do quite quickly formal static analysis of the code. The initial report that we were given actually identified 57 possible issues. A lot of these were false positives. In terms of how we feel about it, I mean, there's a few things that are more exciting than getting an email from someone when you're an open source cryptography developer saying that they've just found a handy new tool that they've developed which can help find CVEs in your code. But anyway, of the 57 possible issues, I think we got about a dozen which are real. The nice thing about the bytecode analyzer was actually able to provide quite specific details as to where the actual problem was appearing and what was causing it. The other thing about it was that a majority of the items, while they were false positives, some of the timing issues were definitely things that had been previously missed. So it would have captured whatever that we'd seen before. It definitely captured things that were new, that we hadn't seen before, which were already in the code. And the presence of all the false positives really told us that it wasn't letting things escape, which was a nice thing to have. But the downside was that there wasn't any mechanism to configure the tool, or there isn't at the moment, to configure the tool and just say, yeah, don't worry about this particular one. So our concern at the moment, I think, from the point of view of usability, is that the tool at the moment is generating quite a bit of noise. So I think for it to be more sort of generally useful, we're hoping that they'll actually do some work on suppression as well. So what we've seen, a lot of the false positives are connected with taint checking. It's very hard to do because basically when you're analysing code statically, you've got no references or context to actually work off as to what's in fact going on. If an input's been passed in, whether it's just a regular input or there's something special about it that could actually pose a risk or whatever to the code, whether it gets exposed to a secret and that, which is really what they're looking for. With constant time analysis, obviously simple branches occasionally are actually necessary, null checks and things like that, which are basic code safety, which will also get flagged. And these are things that, in the ordinary execution of the program, you would not expect those branches to ever get exercised, simply because they're there to make sure everything's working properly. Certainly internally, if people are passing nulls where they shouldn't be, what you're basically establishing is that your code is broken, and those things get fixed. But, we leave tests like that in there in case someone does do something that breaks it. You probably think, all right, if they're using bytecode as the source of truth, I mean, our immediate reaction really when we got the report was, if you're using bytecode as a source of truth, how well does this actually reflect on what the just-in-time compiler produces? Especially if you look at Java, for example, which is a stack-based machine. Most of the machines that Java is actually running on top of are not stack-based in the sense that they have other ways of doing things. Now, we've actually found from experience that really, the tells, as you would like to call them if you're into poker, do actually transmit fairly well into what the JIT does, which was surprising. The other thing about it was that we did find with a few of the things that we were sure were false positives, that when we actually did real analysis, because with a tool like this, I think it's very important to emphasize that, it can shine a light on things, but it won't necessarily tell you everything you need to know. Basically, the handy thing about this is that it actually says, okay, this bit of code here is something that you actually need to check more thoroughly. And obviously a great way of checking that if it's a timing issue is you basically just run it 1,000,000 times and do sampling and see what you get. And we did indeed find that when we just paused with the engineering arrogance of going, my code couldn't possibly be leaking here, and actually tried it, what did in fact show up was that, there were in fact some real timing leaks. The other thing, of course, is that these bugs actually are surprisingly hard to fix in some cases. Essentially, if you're looking at timing channel attacks, you've got things like secret leakage, which is due to values in the secret itself. So branching on that, or perhaps the secret has been used as a source of information for looking up a table, in which case wandering around an array can actually expose timing information. And then finally, as well as that, there's just things like the basic branching and control flow, of course. And then, of course, to make it even more exciting, depending on what architectures you're using, we are used to the idea that machine code, of course, is basically single instruction things. But the reality is, if you talk to people that do chip design, you'll find out that a lot of machine instructions are actually very small micro-coded programs as well. And you will find things like, if there's a 64-bit value and the top 32 bits is 0, you'll actually get different timing executions if those numbers are involved, because the CPU itself will go, I don't need to worry about this bit because I already know it's 0, so I'll just ignore it. Yeah, one of the things I'd say is that, which again is emphasizing this idea that this is a continual process. The thing about this that tells you is that what you've got is a situation where people who are doing things which are useful and helpful can actually make your life an absolute misery if you're trying to write constant time code. So at any point in time when you've got everything running beautifully, you're really only one compiler upgrade from disaster, which does make what's already quite a sort of, I guess, stressful particular piece of coding even more stressful. Anyway, yeah, the tool hasn't really been able to suggest exploit paths, and certainly for the things that we found, there's no need for anyone to panic. But we are definitely working on the basis that if there is something that's actually providing some sort of a signal of what's going on internally, if it's not there, then no one's going to be able to take advantage of it. I don't know if you remember when the first constant time attacks occurred. I think it was Bleckenbacher's RSA in the late 90s. You had to have a TLS server that was up for 1 million transactions, and you had to be able to capture those or whatever to start recovering bits of the private key. And at the time, not wanting to diss the hardware of the day, you know, that the reliability of things generally provided enough protection that, you know, it wasn't very easy to exploit that in the wild. These situations changed, of course. So even if we can't find a way for weaponizing it right now, we do try to get rid of things straight away. As I said before, the other conclusion that we've got with the Robuster, as far as we can tell, is it is because it's so incredibly anal about checking stuff with all the false positives and that, we're pretty confident that it's actually capturing anything that's actually in the code already. As I said, if any of the authors are watching this particular talk, being able to mark stuff as okay would be useful. From our point of view as engineers, yeah, the thing is, you know, it's very easy to dismiss something as a false positive, but it's necessary, I think, if you're using these automated tools to actually check that your hunch is correct, because you will find out that it's not. And then finally, yeah, this is clearly not a journey that will end anytime soon. I imagine we expect that research on these tools will actually continue, and especially a tool like this one in particular, which is in a sense practical, because you can actually apply it to real-world code quite easily. We're kind of looking forward in a sort of apprehensive way to, I mean, yeah, as long as I can avoid jump scares, I'm good with it. I think that's all I'll say. But yeah, we're basically looking forward to seeing this continue, and I think there'll be ongoing improvements basically in what we're able to do due to what the actual tools will report. So that said, are there any questions?
Great. Thank you, David. All right. I don't see any online at the moment, so we'll just handle the ones in the room.
Thank you, David. That was very insightful. It seems that you see the value of formal methods applied to the implementations in Bouncy Castle. I have two questions. First of all, are you planning to use the same tooling on the non-post-quantum cryptography implementations?
Yep, we're planning to apply this to everything. The main reason it's of most interest to the post-quantum cryptography is we had experience with the tool, the earlier version of the tool, incarnation, so to speak, on the post-quantum APIs originally, because that was what the original funding was about. But yes, at this point, if you look at the paper, you'll see that when the paper finally is made available, you'll see that they've actually started to apply it across the whole BC APIs in general, but also the FIP